moment, since we've done quite a few of these at this point, and I think you can figure out the hypothesis that would best suit this situation. And again, like most of our questions, I want to ask you, to ask yourself, is this a proportion or a mean? Think about that as you reread the problem real quick. What are they trying to test? They're trying to test a mean, a proportion. What kind of data do we have? What do you think? Proportion or mean? Proportion too. We see the word percent in there several times over. We also see that the kind of evidence they collected was this many successes. This many people were able to successfully complete in 4 years out of the total number that we examined. So that also lends itself. So what that tells me here, when I say proportion, is that I better have a P in my hypothesis statement. That's what we're testing, a population proportion. I'm guaranteed the equals to there, and then think about how we keep layering in the information. What is it that they want to test? Yeah.
If it's less than 71%?
Yeah, excellent. So you can see that their motivation came from the 71%, and this is also. So the number you use in the hypothesis statement when we're testing these doesn't change. There's one sample proportion tested. This one's 0.71, that one is as well. And like that, you've done step one. Finished. Yes?
Do you only go with the less than sign for the alternate because it says because this just stats that it gave?
No, that's a good question. So the data doesn't lead us to our alternative. I got the alternative, or I assumed you did when you told me, was because they asked, has this percentage decreased? That's ultimately the question they want to answer. So that motivated what my alternative is. I don't even consider what the data is until I get to step 3, and I see how it fits in with what their question was. So I think they're maybe a little apprehensive. Maybe they're thinking maybe it's decreased, and if it has, they're going to want to figure out what it is. So the second step is doing the conditions and assumptions. I'm going to kind of random sample. I'm being a bit lazy today. I'm using some abbreviations. Yeah?
I'm sorry, going back to step 1. The second part of step 1, I guess I wasn't here, unfortunately, last class, but the AJ hypothesis part, what is that representing? The P is greater or less than 71%?
Yes, absolutely. So 71 is what they know historically. That's how it made it up here. And so that's what they know. This is sort of the status quo. And then they're curious if it's decreased.
Okay.
So, I mean, as I said in the last class, this equal to pretty much almost implies greater than or equal to. So you can see that we've sort of taken the situation and put it into two different sort of extremes, right? Either you're greater than or equal to, or you're less than. But for the purposes of our stat book and the software we use, they tend to just write it as equals to. Random sample of independent, thank you. Independent trials. Success, failure, and 10%. So I got them down here. We'll work our way through them. Is it a random sample? Yes. Mm-hmm. Absolutely. For those guys who collected the data must have had a stat class at that university, right? And they knew to collect it as a random sample. Independent trials. Yeah, I would assume each student's ability to finish in 4 years is independent of another student's. Success, failure. So this is basically where you kind of churn out some numbers, n times p and n times q. So we have, what, 1,500? Yeah. 0.71, and then 1,500. Q, that is, unfortunately, the people who didn't finish in 4 years, is 0.29. That's the complement of P. I'm not even going to bother putting these into a calculator. I think we can both see that 71% of 1,500 and the 29%, they're both well above 10. So I'm going to check these out. If you want to put the products there, you may. But our sample size is so large, and this is such a reasonable size proportion for each of them, I'm not worried about it. Last one, 10%. So this is, our sample size is 1,500. So multiply it times 10, and I'm going to think in my population, 15,000 students. As long as I can know that at this university, either there's 15,000 students in any given year, or I would imagine maybe they sampled over several years here. They may not have just used one, recent years. So if they've had more than 15,000 students in the number of years they sampled from, then we haven't chosen a sample that's dramatically too large. So I think that should be fine.
So is that kind of like saying you can manipulate?
Well, not manipulate. I mean,
Well,
clearly if I was
so you
doing
can take
this,
lots of colleges and say they don't have 15,000 students, or they don't have 15,000 freshmen in a year. So
Right,
you're
right.
still kind
well,
of,
if that's the case for a smaller college, then they'd have to have a smaller sample. The random sample.
but what I'm saying is if you have no idea because it just says local university, then you're kind of just like,
Yeah, I mean, in
Making
a
it work.
real world problem, world problem where you apply this, I mean, you're a little more knowledgeable about where they
Okay.
are, what they're doing. So
okay,
you would advise them, okay, you want a sizable sample, but you don't want to have too big of a sample.
right, okay.
So what does this all tell us?
We can use the
So we
normal.
can use the normal.
Use a normal. Use our friend the Z's table and the normal probabilities to solve this. The third step, I am going to draw my normal model since I've been given permission to use it. And we have to think about what ends up in the middle, because I'm really always wanting to label that. And also, what's going to dictate our tick mark, our standard deviation. So anytime I draw a normal model, I want to know what's the center of this model and what's sort of what dictates the width of it. So what goes here?
P.
P.
Mm-hmm.
Remember the null hypothesis, we talked about this last class, is considered true until we can find evidence to say otherwise. So that's part of his sort of feature of being true, is he gets to be the center of the distribution. We believe this is the case. So then we're also going to use P up here in the standard deviation work. P and Q. I'll have to divide that out. Have someone help me? 0.012. Good. About 3 decimal places is a good number to go for these. Now the problem says less than. It doesn't guarantee that my data is going to be on the left. I haven't even looked at my sample data yet. But I am going to just bother for the moment to label the left-hand side of this with the tick marks. You don't have to label the tick marks at all if you don't want. I just think it's a good practice to illustrate what's going on. So if I subtract 0.012 many times over, oh, thank you. 0. What?
698,
Good.
0.686, 0.674.
Excellent. Oh, nice. And we'll find that software will definitely speed this up. It almost makes me obsolete, except that, I need to tell you what the logic is behind it. All right, so this is what I call the scene. This is the world according to the null. All we're going to do is take a moment, and we're going to put our data into the world where the null is true. So I have to figure out what it is. What is p hat?
0.70.
Oh, so it's
It's 1048 divided by 1500.
great. And that's equal to 0.70. Some people might call that 0.699, depending on how much you want to round, or is it?
It was 0.698.
Okay, okay. That's good enough. So this is p hat. Where does it fit in this picture? If we look on the number line, because this is a legitimate number line, it should be,
Just 4.
yeah, right here, just after 0.698 would be 699 and then 0.70. But it naturally fits here, and this is p hat. And I'm going to shade to the left. So we're interested in how likely it is to observe the sample result we did or something more extreme. When I mean more extreme, it means further away. And since we're doing a what we call less than here, or we'll call a left-tailed test. This actually has a name. See how I shaded my tail in? What would you guys call the test we did on Friday? A right-tailed test. It had a greater than the alternative, and when we shaded out to the right. So these are sort of their catchphrases, a left-tailed test. So what I want to do right now, I guess we could kind of use our instinct, our intuition. Do you think this is an unusual finding for the college, a 70%? If this is truly what the population proportion is? No, it's less than 1 standard deviation away. I would chalk this up to sampling variability. Just this sample happened to have a slightly lower than typical. Maybe the next one they do at 1500 might have slightly higher, but it doesn't seem that unusual. It seems quite normal. But I do want to still finish this out and do our z-score and all that. But our intuition is it seems quite normal, so I'm believing that this guy's still innocent and true. So we're going to do a z-score. Remember what a z-score is, especially if you have the picture. It is where did you stop along the axis and begin your shading at 0.70. Subtract off the mean and divide by what you dictated your standard deviation or tick mark distances. This will be negative 0. That's about as much as I can tell you. 8.3.
Oh, I have 6.69, but I have some slightly different.
Did you use a different, we rounded that
Yeah.
sample data up pretty high.
Yeah, it's negative 0.833333.
Anybody else want to give a second on that before I move on? I don't want to do it.
Please stop.
Yeah, I gotta see.
Like, I don't understand why you do all this work when you can just divide
I was thinking the same thing.
1048 by 1500.
I was thinking the same thing.
All right. Hold with me. Ask me that question after we find the probability, and I'll answer that question. He's right. He's right. Okay, good. Thanks. I learned my lesson. Sometimes I'll just take answers when people call them out, and then I do like half an hour worth of work and the answer. It's just off. Never wrong. Just off a little bit. All right. So let's look up. Z equals negative 0.83 in the Z table. And what this does is it brings us to probability. I know it's only less than 1 standard deviation away, but I also want to sort of layer in what the probability would be.
0.2033. 0.2033.
And that's what's in here. So if I kind of make a little space here, I'm asking them for saying, okay, what is the area of this shaded area? 0.2033, and that's from the negative 0.83, right?
Mm-hmm.
That's our probability. It's called a probability value. And don't kill me when you see this, okay? I didn't do this. It's often, in short, referred to as a p-value. That p is short for probability, not proportion. There's a lot of p's in this class. Like 2033. So, in addition to the extremely small z-score, in other words, close to the middle, it will then be complemented with a pretty high probability. Now, typically in this class so far, we've sort of told ourselves to be cautious when we see things that are more than 2 standard deviations away. We've also sort of used the marker of 5%. So, with both ideas, less than 2 standard deviations away, well above 0.05, what do you think our decision is going to be?
That null was correct?
That the null was correct. So we have to retain. So we have 2 things that can happen here. We can retain the null hypothesis, or reject the null hypothesis. I put them both there because I want you to figure out which one's most suited for this situation. And in this case, we're going to retain. So I have to keep this guy. In other words, the trial has been finished. All the arguments were made. The evidence been presented. And the null hypothesis was able to retain its truth or its innocence. It's still the case is that P can still be considered for this college. The proportion to finish in 4 years is still at approximately 71%. Yeah.
So if we drew the next normal model of representing H alternative, it would just be like slightly to the left?
Yeah. And it would look normal. Actually, if we do it to the left, then
Is that right?
right.
Okay.
We do it to the left.
It would just be like the mean shifted from 0.71 to 0.698, basically?
Yeah.
Okay.
And then, you know, it wouldn't look that unusual there, but the fact is that it is
Right there in that.
consistent with the null hypothesis, and because it gets the assumed innocence, you have to stick with that assumed truth. All right, so back to you guys' question. I know you're like, well, it's below 71%. Why are we doing this? It has gone down. Again, it's no more than sampling variability. Right? It's just a little minor fluctuation because of the sample they chose.
Can't you tell that just by looking?
Yes, what the true kicker is that things can fluctuate, right? We know samples change from sample to sample. You learned that with the marbles, right? Picking the marbles up. But this tells you kind of the size of variation that we can have. So each tick mark is about 1.2%. Now if I go beyond 2 of them, typically, then I'm going to be like, ooh, that was weird. So if the sample had been 3,000 students, right, then this is going to shrink. And then it's going to be even easier to be further away. Does that make sense? So we just want to put it in its holistic sense of like, this is how samples of size 1,500 should behave. They should return somewhere between 0.686 and
0.734.
what was this one?
2.2.
2.2. Thank you. So 95% of all samples of size 1,500 should, with normal sort of variation considered, should have a result somewhere between 0.686 and 0.734. And ours fell right in the middle of that, so it's not that unusual or overwhelming. It's not compelling evidence. But say something did fall back here, let's say 67% even, that would be weird. That would show, hey, wait, that's not typical. That would be very unusual. And that would lead us to believe that maybe things have changed. Maybe no longer they can say that 0.71 is, sort of their bragging point for their college. This is a pretty high percentage for people to finish in 4 years. It's not an easy task to finish in 4 years. So, I don't know. So if they're wondering that they put this in their brochures, maybe they've put it on their website, right? So sort of a, we can say 71% of our students can finish in 4 years, which is attractive to a lot of people. They can continue to say that. They've done some research and they're like, okay, we've done some recent research and this number still stands. We haven't found any contradictory things to say that otherwise. Yeah?
So the retaining the hypothesis saying that the number hasn't changed.
Right. We're keeping the null. And the null says P is approximately or is 0.71.
Even though when you divide it, it's like slightly off?
Slightly off. But again, we're just saying that's just natural fluctuation.
Okay.
You need to be compelling evidence. You need to make a clear, significant separation from the 0.71 for us to start to doubt that the null hypothesis is true.
Gotcha, okay.
Yeah. So let's talk about this decision a little bit more. We'll take the opportunity with this question. So we'll write our statement down here in a minute. But I'm going to create some space, and I'm going to talk about something that's going to help us make a decision. Otherwise, you can see it's just sort of like, well, it seems unusual. So what we're going to talk about is something called a significance level. This is in the notes in that middle page. And the significance level is called alpha. And this is a little a in the Greek alphabet. He actually wears several roles in this process, but then this one, he is what I call, alpha, I call my threshold of weird or strange or rare or unusual. You get where I'm going with this? So slash, this. So in some fields, 5% is that sort of probability. Anything that happens below it, they're like, oh, that's surprising. But in some other fields of study, they want things to happen less than 1% of the time before they feel like it's a surprising outcome. Some fields of study, they're okay with 10% of the time. Anything that happens less than that, they're going to call that an unusual occurrence. So it's sort of a moving target depending on what field of study you're in and what people are comfortable working with. So alpha in our problems will be declared. When you get one from me that's not from the notes, you're getting a homework assignment to finish. I'll give you a due date later. These things are declared in our problems. So they're usually declared within the text. Let me here just say let, for our problem, alpha equals 0.05. In other words, 5%. When we get to the last page of the notes, you'll find that there's another role that alpha plays, but right now I'm focused in on this significance level. So how does our, again, alpha is a probability. How does our probability, our p-value as we're going to call it, compare?
Greater than alpha.
It's greater than alpha. And we decided when it's greater than alpha, we retain. So if you look in the notes, there's that little sort of weird section there. Looks like it has a little comic book symbol around it where you see POW or WHAM or whatever, a little goofy looking thing out there around it. That's a decision. I put it there to just draw attention to it. And it says, if your p-value, probability value that is less than or equal to alpha, reject the null hypothesis. Otherwise, I can write it this way, if the p-value is greater than alpha, retain. The same thing we've sort of discussed in class, but we've never formally written it down. This is that goofy thing in your notes, right? I may have paraphrased it better in the notes. And believe it or not, this decision criteria will be the same for Chapter 8 and Chapter 9. It's the same criteria for means or proportions. It doesn't matter what you're testing. That's why we like to bring it down to this probability value to test things and make our decision, because that way you don't have to remember all these different rules for all these different situations. We can just bring it to probability, and probability will answer your question. So in our case, if we write them side by side, our p-value, I even shorted it p-val, so yeah, they would put it, you'll see people write it even shorter, of 0.2033, and if we put alpha next to it, we can make a side-by-side comparison. Now, some students don't need to do this. They can see two different quantities on separate parts of the page and figure out who's smaller. But then some students who aren't that great with numbers need to put them side by side an exercise that we did when we were in elementary school, the alligator, right? And figure out who's bigger, who's smaller. Right? The alligator always wanted to eat the larger quantity. Which one's larger?
Yeah.
I know it seems elementary, because it is. There. So that inequality is put in based on the size of these two numbers. It has nothing to do with the alternative. The p-value is greater than alpha, thus, what are we told to do? Retain the null hypothesis, which is what our intuition told us to do earlier. So you can still have intuition, but if you don't like intuition, I hate to say it, this rule you can memorize and stick with it for the course of the semester. Yeah.
Does alpha always have the same value for stuff?
It'll change. That's a good question. So in some problems, you'll see that alpha's been set to be 0.01 because they want their threshold of weird to be less than 1%.
Okay.
So it'll be something that's given to you in the problem.
Okay.
Oh, the alpha is?
Yes.
Okay, that's what I was wondering how you got that.
Yeah, I just chose the 5% because it's something we work with often. But I'm about to give you a homework assignment at the end of class, and in one of them it's 5%, on another one it's 1%.
Will it always be given, or should we assume it's?
In exercises that I give you, yes.
Okay.
In a project, you might decide what you want your own alpha to be. And I think this is a good time to discuss the back page. I'm going to try to skip that middle example. We can always come back to it because it's a good time to discuss it because we're sort of sitting there going, okay, sure, alpha seems great. So let's write this statement. I should at least do that to finish out this problem, and we'll discuss alpha a little more. Someone help me with this statement. The lingering question was, has this percentage decreased? Right? That's sort of how they left the problem. And you can't just write no. I wish that were it. But you want to sort of summarize. So I like to start with the sample data or the sample evidence, because that's what we use. What did the sample evidence tell us? Did it support or not support this notion of decrease?
It doesn't, right?
And it didn't decrease. So the sample evidence does not support.
So if it's not in the alternative, it does not. If the answer is
The
wrong,
data
it
did
does
not support, right, so yeah.
Sorry.
Sample data does not support the notion, the claim, the idea. I want to put claim here. That the percent, I might as well write that out in the word. Percentage of students completing degree in 4 years has decreased. So that evidence doesn't support the idea that it's decreased. So here's the idea that we're not going with the alternative.